So we're going to do another problem today. This one, I don't think we've done one quite exactly like this one yet. This is a problem where we have a few kind of different elements. For one, we have a linkage. We also have friction that we've got to take into account. We've got, we have to evaluate whether or not this thing's going to slip based on that friction. So there's some pieces here, and this is kind of there's nothing particularly new about what we're covering here. We've done all of these pieces before, but we haven't quite put them together in this exact arrangement just yet. So we should probably get started. All right, so we have this block. You can imagine this block as having that shape in and out of the page, a quarter circular shape. It weighs 100 kilograms, and it is going to be lifted with the mechanism that's shown right there, the little linkage. The links have masses that are proportional to their lengths, so 10 kilograms per meter worth of length is how much each of the links weighs in that mechanism. We're going to neglect friction in the joints, in the pins that happens here. We can assume also that all of the members are perfectly slender, so we can do that with respect to finding moments of inertia. We can also do it with respect to the idea that, if we didn't think of them as perfectly slender, then we might doubt whether or not the surface where the friction was happening was in the same plane as pins B and D, for instance. We're going to ignore that. So we're going to assume that that's small enough that it's a negligible effect. All right, and at the instant when we have theta equal to 65 degrees, we're going to assume that at that instant our omega, the angular velocity that's shown on there, is 85 degrees per second. And what we want to find are a couple things. First of all, we want to determine what is the maximum allowable angular acceleration alpha that we can apply while having the block not move relative to link BD, okay? And we're going to assume there that our coefficient of static friction is going to be 0.6, okay? And for that question, we're basically saying we don't want it to slide and we don't want it to tip. We want it to kind of stay put on that link BD. In the next half, we're going to determine how much torque we have to apply at pin A to actually achieve this angular acceleration alpha that we found in the first part. And then under that torque and the motion of everything else, we want to determine the magnitude of the force carried in each of the pins in the linkage. There's 4 different pins there. We're going to try to figure out the force magnitude in each one of those pins. All right, so the big first thing that I need to discuss here is we're given some information here. We're given that links AB and ED or DE, those two links are the same length and they are parallel with one another. If I know that they're the same length and they're parallel with one another, what can I surmise about the motion of link BD? Okay, well, here's how you can kind of think about that. Because you know that point A and point E are not moving, right? Those are fixed, right? They're not translating, okay? Because of that, I know that whatever velocity I have of B, it had better be perpendicular to the orientation of the link itself, okay? And because those two links are the same length and they are parallel, those two velocities right there are going to be parallel. And if those two velocities are parallel, that means that we have a pure translation, okay? One way of thinking about that is if you were going to try to find a radius of curvature, right, using like an instantaneous center of zero velocity kind of a method. If you were going to try to do that, you really couldn't, because the lines of motion there, the lines of those two velocities never intersect because they are parallel with one another, okay? And so that's really a really big thing that we need to know going into this. What that tells us is that any point on member BD, and because we don't want the block to move relative to BD, it also means that any point we pick on the block, it also has to have the same acceleration vector and velocity vector, regardless of where we look in that whole body. Okay, that whole body including link BD as well as the block that's sitting up there. All right, so that actually allows us to do a lot more with the block all by itself than we could otherwise do, perhaps. Okay, so that's where I'm going to start, is by looking at the block itself. Okay, because what we're supposed to find is how much alpha can we have so that the block doesn't slip or tip, right? And so, you know, it seems fairly intuitive that we would start there with a free body diagram of the block itself. So that's where I'll start. Okay, so here's the block. Okay, and often when you're doing these kind of tipping or slipping problem type of things, you model the force that's on the base of the thing as two forces, one on each end. All right, so I'll just model these like this, where I call this maybe FR for the right-handed force, the one on the right-hand side of the piece, and then I have another force over here that's on the left-hand side. Okay. The other thing I can say is that I've got a frictional force, and based on how this thing is moving and how it's accelerating, my guess is that the block is going to have to be accelerated leftward. All right, because the block has to be accelerated leftward, that probably means I need a leftward pointing force due to friction right here on the bottom of this body. Okay, so I'll call that, for now let me just call it F sub lowercase f, like this, for a frictional force. All right. All right, so those are a few of the forces that act on that block. What else can I do on this block? Okay, well, I know where the CG is for the block, and I won't spend time looking it up per se, but I will represent to you that you can find this by if you know the, say, the radius of this quarter circle, which in our case is 3 meters, then you can figure out where this is located based on 4r over 3 pi. So for us, r is 3 meters. Okay, so that's where that height is, and because it is symmetric about a line that's 45 degrees going up right there, that is also the value that we would have going over here, if that makes sense. Okay, so that's where that is located. That's the center of gravity. Do I have any forces that act at the center of gravity? Okay, assuming this thing is in weight, right? It's in a gravitational field, right? It's got weight to it. Assuming that, then I would say it better have that weight represented on here, and that weight can be represented by mass times gravity. Okay, and I'll just call that mg for right now. We can plug in the numbers later if we need to. All right, so far so good. That, I believe, covers all of the forces that we would need to put on the free body diagram of the block. And I think I showed y'all last time that we could also represent the kinetic diagram on the same picture. Okay, this is up to you. You can draw two different pictures if you want, but it actually doesn't hurt you necessarily to draw everything on one picture, especially if you are using colors, right? If you have some way of differentiating between the different vectors that you draw on the picture, that can help out. And so I will do that on here. we have a couple of different accelerations that we can identify for that center of gravity right there. Okay, one of them is a, what I would kind of refer to as a tangential component of acceleration. Let me just put that up here like this. Okay, I don't know what the value is yet of that tangential component of acceleration, but I can relate it to the alpha that I have identified right there at the beginning of the problem. How can I relate it? Let me ask this. If I know alpha, can I determine the acceleration of point B? Okay, how do I figure out what that acceleration is of point B if I know alpha? Okay, yeah, I've got equations for that. The tangential component of it, right, which is what I really should probably put here, is the tangential component of that acceleration of point B. How does it relate to the tangential component of the acceleration of point C, which I have representing the center of gravity of the block? How do those two relate to each other? They're the same, right? Since it is translating, all of the points have the same acceleration, right? Which means that I can say that up here, this acceleration is just going to be equal to alpha times 2 meters. That's the formula that I've got. I can take alpha times r, basically, and get an acceleration at a particular point, a tangential acceleration at that point. All right, so far so good? All right, but that's not the only acceleration I have at point C. Why not? Yeah, I have a normal acceleration because I have a non-zero angular velocity of point B, or of link AB as well, right? I'm told there that I have an angular velocity of 85 degrees per second. That means that point B accelerates toward point A like this according to what equation, or what kind of expression? Yeah, it's centripetal, right? Which means that you can take that angular velocity and you can multiply it or you can square it and then multiply it by r. Okay? And so because I'm going to get kind of messy down below here, let me just show this arrow like this. Okay? And I'll call that omega squared times 2 meters. Okay, but I know what omega is, right? I'm given that at the very beginning of the problem. Omega for link AB is 85 degrees per second, and so I may as well put that in here as 85 degrees per second. Okay, why don't I go ahead and work this a little bit? If I change this to radians, what I do is I have to multiply by pi over 180. Okay, and I could then multiply it by 2 meters like this, and this is just a constant value that I will have for all of my kind of normal acceleration terms that I end up with here. That's how I figure it out. So let me go ahead and just get that in here real quick. Okay, let's see, 85 degrees per second squared, and I should have put that on here. All of this right here should be squared. Okay. All right, so I have 85 times pi over 180. And then this is going to be squared, and I'll multiply it by 2. Okay, so this acceleration that I have here is just going to be 4.4017. Okay, and that's going to be in meters per second squared. Okay, and because I might want that later, let me go ahead and store it into y. All right. I kind of just took a minute there, and instead of working on the main root of the problem, I got that value kind of calculated there. All right. Now what should I do if I'm trying to figure out my alpha value, right? That's what my first part of the problem is what's my maximum allowable alpha that I can use to get, or that I can apply and still have the block stay there. Okay. All right, so I think maybe what the recommendation here is that we can sum moments for this block, and I don't actually see much of a reason why I would have to sum around any other point besides the center of gravity. So that's, I think, a good recommendation. We can take this block and sum moments around the center of gravity, which I've called their point C. Okay, so what kind of forces do I have there applied around the center of gravity? Or what moments do I have applied around the center of gravity? Okay, yeah, I think I heard someone maybe say the left force. Okay, that I'm putting a negative there because it's putting a clockwise moment around the center of gravity. What's the length between that force and point C? Well, for this one, it's probably going to need to be 3 meters minus 4 times 3 meters over 3 pi. Okay, what you see there is that the overall width of this thing is 3 meters. And so if I take that 3 meters and subtract the amount that I identified a second ago that gave me where that CG was, then that gives me what the length is from the line of action of FL to the center of gravity of the block. Okay, what else? Okay, plus FR times what? 4 times 3 meters over 3 pi. Okay, so far so good. Any other forces that create moments around the CG? Yeah, friction. Okay, now here's where I should probably work on the friction a little bit. Okay, at this point, like, you know, this is a key point that I need to make. This is a special kind of problem where we need to take that alpha right up to the point where it's about to slip, right? And we actually know, based on the static coefficient of friction, you know, what that is going to be relative to FL and FR, right? All we have to do is say this is going to be equal to the sum of FL and FR multiplied by what? My static coefficient of friction.
How did you know that?
Okay.
How did you know the sum?
You sum them because that's basically, you can think of it this way. You can think of it as, let's say that you imagine 2 patches where you have contact at the left end and at the right end.
Oh, that's
Well,
kind of like the normal force.
right.
Okay.
It's another way of saying it's the normal force, but that's what it ends up being. Yes, sir.
So if they equal, wouldn't it slip? Or is it at the point right before it slips?
Right. So if we make it equal, one of the words or the phrases that we use sometimes for this is impending motion, right? This is the threshold where it might start to slip. So you take it up to that alpha, then you're in trouble, right? Or you could be in trouble because it may start to slip at that point because it's right there at the threshold, which is what it's asking for, right? So, I mean, it's a point well taken that if you take it up to that, couldn't it slip? And the answer is yes, that is the threshold where you expect that it might begin to slip. We should probably put some some asterisks around that and say these static and kinetic coefficients of friction are not as, like you can look it up, look up typical static coefficient of friction or kinetic coefficient of friction for material pairs. Those things are not as deterministic as we make them out to be sometimes. Okay, means that a lot of conditions can affect what that value actually is. All right, so put those asterisks around it. We're going to assume that this is right, 0.6. Okay. All right, so now we take that force, FL plus FR times 0.6. Okay, what direction does that tend to try to rotate the body around the center of gravity? Clockwise, right? Which is opposite of my positive direction. So I'm going to take that to be minus. Here I'll put FL plus FR. Okay, times 0.6. And then what do I need to multiply by? Because right now that's still just a force, right? And I'm summing moments. So what do I need to also multiply by? I need to multiply by how far it is from where that force is acting to the CG, the point around which I'm summing moments. And because, again, both the height from the flat down here and the distance left from the flat over here, they're both the same, I just multiply this again by 4 times 3 meters over 3 pi. All right. I think that takes care of all of the force values that I have that create moments around the center of gravity. What do I set this equal to? Okay, generally speaking, I would set this equal to the moment of inertia for that body, for this quarter circle, times what? I sub g times alpha. Okay, so that means that we need to think about, do we have an alpha for this body? What do you say? Do I just use the alpha that I have for link AB and calculate a moment of inertia about the center of gravity, or not?
0 alpha.
Okay, someone says 0 alpha, right? You want to use 0 alpha because it is a purely translating body. It is translating through a curved path, but it is still just translating. It is not rotating as it translates. And so that means for the sum of moments that we use here, we can just set it equal to 0. I'll give myself just a little bit more room there where I can do that. All right, so there's my first equation. Can I do anything with that equation before I move on? How many unknowns? Yeah, I got 2 unknowns there, so that makes it to where I probably can't solve for anything just yet with that one equation. All right, so what other equations can I write? Okay, I can sum forces in the x and y. Okay, which I think that's a good idea. Let me sum forces here. Maybe I'll start in the x direction here. Okay, so in the x direction, I have a leftward force of FL plus FR times 0.6, right? So I have a minus FL plus FR times 0.6. Okay. Any other horizontal forces that I have on this body? Okay. Doesn't look like it to me. So what do I set this equal to? Okay, I need to set it equal to the x component of acceleration. Okay, and so I can find what that x component of acceleration is by combining the x components that I have from my alpha component that I have there, the kind of the tangential component, and the normal component, the two that I have written up there. And here's how that would look. Okay, let me actually first identify the angles that I have up here. So if I had, let me ask this, if I had a theta value that was 0, what direction would my alpha times 2 meters be pointing? If theta was 0, it'd be pointing straight up, okay? Which would, that would indicate to me that if I measured theta, I should probably best measure that right here, right? Because that would, when I make theta go down to 0, that makes that vector point straight up, okay? And I know these two vectors are perpendicular to each other, so another thing that I can do is I can say, this right here is also theta. And, drawing it on there like that is helpful sometimes because then it helps you keep it straight. All right, so how much contribution do I have to horizontal acceleration that happens due to my tangential component, right? This is my tangential component up here. Okay, well, what I would end up having is alpha times 2 meters, all right? That's just my linear acceleration in the tangential direction. But I don't want all of that. I just want the component that's pointing in the horizontal direction, right? And let me actually make this negative as well because it points leftward. I need to multiply by the sine of theta. That allows me to pick off just the horizontal component of that piece. All right? So that's what I see there. And let me actually also add on to this, because that's the total acceleration that I would have due to that component. Let me also put on there the component that I have from my normal component, which is just going to be 4.4017. Okay, that'll be in meter per second squared. But I don't want all of that. Okay, what do I want? Just the component that points in that leftward direction, right? So I would need to multiply this by the cosine of theta. All right, I'm running out of room. Let me go down to the next line down here. All right, so that's what I've got so far, but that right now is just my acceleration that I have of the center of gravity moving leftward. Okay, what do I need to do to complete this formula or this equation? Okay, I need to multiply it by the mass of the body, right? And the mass of the body is 100 kilograms from up here. All right, so now let's, for just a second, look at our system and say, are we any better now? Okay, now we have FL, FR, but now we've introduced this other variable alpha as well. So now we have 2 equations and 3 unknowns. So we need to do our last equation. Okay, in the y direction. Take upward to be positive here. Okay, so what do I have for my forces in the y direction? Looks like I have FL, FR, all right, what else? Minus mg, that's the weight, so that's minus 100 kilograms times 9.81 meter per second squared. Okay, any other forces in the y direction? I think that looks like I've got everything. So I'll set this equal to the acceleration I have in the y direction. Okay, so kind of looks similar to the acceleration I just figured out in the horizontal direction. Okay, I just need to make sure I get my signs right. Okay, so my alpha term looks like it does generally point upward, right? So I would say plus alpha times 2 meters times the cosine of theta by the way, I know theta. I'm just putting it, I'm writing it theta in there, but what is theta? Yeah, theta is 65, so I can introduce that whenever I get ready to, punch in all my numbers and values. All right, so that gives me my acceleration vertically due to that tangential component of acceleration. Then what? Okay, minus 4.4017 meter per second squared. Okay, for this one, I want to multiply it by the sine of theta. And all of this stuff is also going to have to be multiplied by 100 kilograms. So that I fulfill my F equals ma. All right, so now let's look at our system. How many things do I know? Okay, well, how many things don't I know, right? How many unknowns do I have? I don't know FL, I don't know FR, I don't know alpha. And so that, fortunately though, I do have 3 equations, and they are linear equations, and so it's not that hard for us to pop this in and determine what those values are. Okay, and just kind of in the interest of making this a little bit more brief, let me just give you what those turn out to be. Okay, so those turn out to be FL ends up being 116.755. Newtons. Okay, FR ends up being 570.989. Newtons. And alpha is 1.25025. All right, and that is radians per second squared. Okay, you have to always be careful of that. The comment was sometimes it's easy to write a summation and set it equal to 0 inadvertently. Being in a dynamics class, that's definitely something we have to be on guard for. But I mean, you remember that just a few meetings ago I did the same thing, right? I was working something and I just quickly set it equal to 0. I had my brain in statics mode, and you just kind of have to pop your brain into dynamics mode, because it will sometimes be 0. Like for instance, this one right here turned out to have all of our moment terms summing to 0 because it happens to be a pure translation, right? So sometimes, yes, that will happen, but we have to be very careful and not ever assume that's what's going to happen. Yeah.
I think everything was quick. So the reason that we set everything equal to 0 in the sum of moments equations is because all of your accelerations flow through the center of gravity?
Yes. So the comment was the reason that we can sum all of my moment terms, or all my sum of moments equal to 0 here, is that all of my forces have lines of action. Let me back up that. It's not that all my forces have lines of action through that point. It's that I am taking the sum of moments around the CG. When you take sum of moments around the CG, it is just purely equal to I alpha, right? We know that alpha is 0 because we know it's purely translating. Okay. So we always assume that the CG is the point that is actually accelerating, like the linear acceleration is applied to the CG. So that it isn't so much a coincidence, it's that's how it works, right? You add up all of your forces, and that will lead to you knowing what the acceleration is of the CG of the part, right? So that it's not really a coincidence, it's that's the way it's always going to work. Okay. Now, having said that, we summed moments here around the center of gravity. which means that we did not have to take into account any of those extra kinetic moment terms. Remember that how we covered that? We didn't have to take into account any extra kinetic moments terms. We are, you know, in a few minutes here in the same problem, we are going to get into one where we will need to take into account an extra term like that. So
how is it alpha is not 0, like for the x and the y?
well, alpha, so you have to be very clear about what alpha you're talking about, okay? The alpha that I have drawn on this diagram is, you know, like for the tangential component, for instance, right here. The reason that I have this term of alpha is not that there's an alpha for the quarter circle part, it's that there is an alpha for link AB, and I can relate that to what that tangential linear acceleration is of point B, and because I know that this whole thing is just translating, I know that that's also the same acceleration that I have in the tangential direction here, right? This and this are the same, right? So the alpha that I have there is the alpha of link AB, not the alpha of the part itself, the quarter circle itself.
I think that was my problem because it was like that block isn't moving sitting on that bar, so it seems like the summation of x would equal to 0.
Right.
You're talking about those little sidebars that are
Right, but that whole thing is accelerating, right? So that's where those values come from. All right, good. We actually just now finished part A, and we have these other couple of values here, FL and FR, that might be useful to us as well. So we've figured out what's our maximum allowable alpha that we can apply to link AB and not have the part slip. And I think I mentioned a second ago, I'll say it again, because both FL and FR are positive values, what does that tell us as far as how the block, like, let me ask a little bit, just go ahead and put it out there this way. Is the block at risk of tipping? Okay, the answer is no, it's not at risk of tipping because both of those values are positive. If I had done all this and one of those values had turned out to be negative, then you can probably surmise that it would not slide, it would tip instead. Okay, but they did turn out positive, so we're good. We can assume that it will slide first. Okay. All right, so let's move on to part B. The torque required at this instant to achieve the alpha that we just found and the force magnitude carried in each pin. I'll go ahead and tell you it may not be best for us to find those in that order. Okay, so I'll show you what I mean by that here, because looking at the rest of this process looks pretty intimidating until you find where you have the least amount of things you don't know. Okay, like you find the places where you're like, I think I can find the things that I need to know. So let me slide all this down. All right. And let me draw your attention to link DE. Okay. What do I know about link DE? Actually, let's just draw a free body diagram of link DE, okay? Because that's a good way for us to enumerate the things that we know about link DE. Okay. All right, so there's link DE. What kind of forces might I have at point D? All right, well, let me actually start here. If you are not in dynamics mode, it's very tempting to look at link DE and say, two-force member. Okay? It looks to me like it's connected only at its ends with frictionless pins, and so we would say, yeah, that looks like it would be a two-force member. And it would be if this was a statics problem. It is not, because it is a dynamics problem. Okay, that is no longer a two-force member because now we have some accelerations that we have to consider. Okay, So, having said that, I cannot just assume that the force in member DE is directed along a line from between one pin and the other, okay? Because I can't assume that it's a two-force member anymore. So I need to actually show two components of force, for instance, at point D in order to fully account for all the different possibilities. There's a couple ways I can do that. I can show, for instance, like an X component and a Y component of force at D. That would be kind of the standard way of doing it. What I want to show you here is a little bit easier way of doing it, but it's a little bit tricky. I mean, it's just a little trick. Maybe it's not tricky, but it's a trick that if you know about it, it helps you out. So I can actually show the forces applied to point D such that they are aligned with the direction of the link itself. Okay, so let me show those here as a force that I have acting on D pointing this way, okay, perpendicular to the member, and let me call that FDT. Okay, what do you think the T might stand for? Yeah, like tangential, right? Because it's moving. We know that the point down here at the bottom has no velocity or acceleration, right? That point is fixed because it's in a bearing. Okay, so I have that, and what else do I have acting on point D? Okay, I also have what I could call FDN, for instance. All right. So far, so good. Let me do that same kind of strategy for the pin at the bottom. Okay, the pin at the bottom, let me call this force right here FET. And let me show another force that acts up along here, and I'll call that one FEN. Okay. All right, what other forces act on link DE? Let me put those letters up there as well so that we can, this is D, this is E. Okay, what other forces act on DE? Well, it has weight too, right? Okay, and you know, again, I can just call that like mg, but this one has a different mass than the block, right? So we know here that the mass of that link is going to be based on 10 kilograms per meter of length. So that means since it's 2 meters long, it's going to be a 20 kilogram link, and that means that that would be 20 kilograms times 9.81 meter per second squared. But I'll just leave it as mg for right now. All right, what else should I put on here?
The force of the rod BD on point D.
Okay, I think I've already got that in the form of two components, FDN and FDT, right? Well, let me do this actually. Let me say that because point D is connected to link BD, and every point on BD has the same acceleration. Would you agree with that? That means that the same acceleration that I applied to point C, I can also apply right here. It means that this point right here has an acceleration to it that is going to be alpha times 2 meters. But now I know what alpha is, right? Because I solved that already. We know what alpha we're driving all this stuff at. Okay? What else do I know? Okay, I know that the acceleration in the normal direction acting on point D, or you know, that point D moves through, is going to be equal to that forgot what it was now, 4.4017 meter per second squared. okay, in case that helps us in some way. All right. So far, so good. I can put some lengths on here. Okay, I can say this is 2 meters. We can say it's 1 meter up to here. All right. Well, why don't I actually do this? Why don't I go ahead and start by summing moments around point E? Okay, again, I'll take counterclockwise to be positive. What's nice about summing around point E is that I eliminate 2 of my things that I don't know. Actually, I eliminate at least 2 of the things that I don't know. How many do I really eliminate? 3. Which other one? FDN, right? The force at D in the normal direction. I eliminate that one as well. Okay, so this is nice because with one equation, I'll actually figure out that I can find f dt. Okay, so we'll go ahead and start putting those in here. So let's say I've got f dt, summing moments here. I've got f dt multiplied by what? 2 meters. Okay, FDN isn't in there, FEN isn't in there, FET isn't in there. Weight is in there, right? Clockwise, the mass is 20 kilograms. Gravity is 9.81 meter per second squared. Okay. Now what? Okay. I'll tell you how I look at this. I look at this as looking at right here and saying that this angle right here must be my 65 degrees. Okay, again, I do that the same way where I imagine it being at 0. Does that angle go to 0 if this thing was all the way laid flat? The answer is yes, it would, right? So that angle is going to move appropriately with it, okay? So that means that if I take mg times the cosine of theta and multiply it by 1 meter, okay, so cosine of theta and multiply that by 1 meter. Okay, that is going to give me the moment created by the weight. All right, what next? Okay, so far, that gives me, I believe, all of the moments that are produced around point E. So now what I want to do is go to another little trick that's helpful to us a lot of times. Remember that if you're dealing with a pure rotation, you're dealing with a part that rotates purely, right? It is possible for you to figure out what the moment of inertia is around the axis of rotation rather than around the center of gravity. Is that true? We did a problem like that, I think, earlier, right? And what's nice is that for a slender rod like this, that formula is actually given in the back of your book. So it basically turns out that instead of being ml squared over 12, it's ml squared over 3 if you're taking it around the end of a rod. And so all we have to do here is do 20 kilograms times the length of this thing is just going to be 2 meters. Okay, and that term that I have written right there is the moment of inertia about point E. So I'll put that note up here real quick. So this thing is I about point E. Okay, but that's not enough yet, right? What else do I need? Well, I actually happen to know alpha as well, right? Alpha is going to be the same for this body ED there, as for body AB. Okay, so I just multiply it by alpha, and I actually happen to know alpha. Okay, alpha was 1.25025. Radians per second squared. And you'll find out here that we have a equation in just one unknown, which is nice. That means we can solve for that one unknown. Okay. All right, so we'll do that this way. We have x times 2 minus 20 times 9.81 times cosine 65 times 1 meter, I don't need to put that in, is equal to 20 times 2 squared over 3 times 1.25025. Okay. And that tells me that f dt is going to be equal to 58.13. Let me do it this way, 58.129, like that. All right, well, is there anything else I can get off of this free body diagram? Answer might surprise you. Yes, there is. Okay, before we go on to anything else, there is one other thing we can get off this diagram. What if I sum forces in the tangential direction, or that transverse / tangential direction? What if I do that? Okay. Well, what I have there is FET plus FDT, which I now know is 58.129 newtons. All right. Minus mg, so m is 20 kilograms. G is 9.81 meter per second squared. Okay. I just want the component that is in the transverse direction, right? Or the tangential direction. So I would multiply this by the cosine of theta. All right. Now what is this going to be equal to? This is going to be equal to the acceleration in the tangential direction of the center of gravity of the rod. Which I don't have that drawn on here yet, but I could put that on here, right? I could say here is the tangential component of linear acceleration of the middle of this rod. Do I know that value? I might not know it, but it's easy for me to express. All it's going to be is alpha times 1 meter. How do I know that?
Because your tangential force at 2 meters is just alpha times 2.
Okay, yeah, the tangential component of acceleration anywhere along this is just going to be equal to alpha times the radius away from the center of rotation. Okay, so since I'm 1 meter away from the center of rotation, I just take that alpha times 1 meter, and that means then that I can say this all is going to be equal to, put it down here, alpha, which is just 1.25025 radian per second squared. Okay, times 1 meter. Okay, and that gets multiplied by what? Mass times acceleration, right? So you need to multiply it by mass, and I need to use the mass of this part. So that's going to be 20 kilograms. Okay. So when I punch all of this stuff in, I can determine what that tangential component is for the force in pin E. Okay. So I do that like this. I'd say x plus 58.129 minus 20 times 9.81 times the cosine of 65 degrees is equal to 1.25025 times 1 times 20 kilograms. Okay. And that ends up giving me 49.794 newtons. Okay. As a big picture thing, so that we understand what we just did and why we could get these things, this is basically how this member deviates from being a two-force member. These are the forces that make it not a two-force member. Okay, so that's what we just did. And the fact that it's accelerating angularly, that's what enables this, these two values to pop out at this point. All right, can we get the other components, FDN or FEN, yet? I only have one more equation to use, okay? So the answer is no, not really. I don't really have any tricks up my sleeve yet on how to get FDN or FEN until I start doing a little bit more analysis. But that's okay. I can go ahead and look at another free body diagram, because there's a couple more free body diagrams that it definitely is likely to be helpful for me to draw. One of them is link BD. Okay, let me draw a free body diagram of link BD. Trying to make these plenty large. I think that helps us kind of see everything on them a little bit better. All right. So what kind of forces do I have applied to member BD? Okay. Yeah, I have those forces that I had down here, right? I have FL and FR. Okay. FL is 116.755 newtons. Okay, I also have another force that happens right in the middle, and that was the FR, right? FR was 570.989 newtons. Okay, what else? Weight. Okay. Anything else? What would Newton's third law say to us about what's going on at point D? Right. For every action, there's an equal and opposite reaction. Okay. That tells me that where I have FD pointing up and to the left at point D right here, it means I better have FDT pointing downward and to the right here. Okay. And that's actually a force of 58.129 newtons. Okay. What about FDN? I don't have that one solved yet, right? I don't even know what a value is, but I know that if I have an FDN applied to D on my last free body diagram, I better have it on this one as well, because it's, you know, it's coming from this link BD, right? So if it points downward to the left here, it better point up and to the right here. Okay, and I'll just name that FDN. All right, what else? Yeah, I can do the same thing over at joint B, all right? And at joint B, I'll show one going up like this, and I'll just call that FBT. And I'll show another one going up like this that I'll call FBN. Okay. Do I have everything yet? Still missing one, it looks like to me. Okay. Friction. Good. Yeah, we had that frictional force down here that was pointing to the left. That tells me I have that force, and I'll just show it right in the middle. That way it acknowledges that I said don't think about any sort of a thickness to this, right? So I'll just show it right in the middle, pointing the opposite direction of what I had originally. And that's just going to be equal to FL plus FR times 0.6. Okay. All right, so those are my forces that I have acting on member BD. This is B, this is D. All right, what should I do as far as kinetics are concerned? Well, it might be of concern to me what the center of gravity is doing. Okay, so let me actually look at the center of gravity of this body and identify the accelerations that I might have at the center of gravity. They're the same as the accelerations that I had at point C or at point D, because all of that is translating, right? So that makes it possible for me to just immediately put on here that I will have this tangential component of acceleration. That's just going to be alpha times 2 meters. And I will have a centripetal component of acceleration. And that one is going to be equal to that 4.4017 meter per second squared. All right. I should put some lengths on here maybe too. So it's 8 meters all the way across. Okay, 4 meters from this end, or either end, and so on. What about this force right here? Kind of that left force. What's that length? Well, this is a quarter circle where the radius is 3 meters. And if it's 4 meters from the left end to the middle, and if the right edge of the quarter circle lines up with the middle, then that means I can take basically 4 from B to the middle of this beam, subtract 3, and that tells me this is just going to be equal to 1 meter. All right. So far, so good. Do you see any equations that would be real easy for us to solve quickly? All right. Someone says some moments around B. That sounds great to me. Some moments around B, that eliminates FBT and FBN. All right. So let's do those. Counterclockwise being positive, it tells me that I first have this FL of 116.0 0.755 newtons times 1 meter. Negative, right? Clockwise. All right, then what? Does my friction force create any kind of a moment around B? Nope. So I leave that one alone. Then I have a couple of forces that happen right at the middle of the beam. I have the FR, so that would be 570.989 newtons. Since they act in the same place and in the same direction, I can just add that on to my weight as well, right? I can just take this and add to it the mass. What's the mass of this beam? Okay. Yeah, 10 kilograms per meter of length, 8 meters long, should be 80 kilograms. Times 9.81 meter per second squared. I'm adding those forces together because they act in the same location in the same direction. All right, so I can just add them straight together. All right, and then I need to multiply them by what? 4 meters. Okay, so far so good. Now what? Okay, I tell you what, we need to also probably get a couple of angles identified on here to make this easier for us to see. That 58.129 Newton force up here acting on D, we can maybe take a hint from our last one and how those lined up, or maybe not, I can't remember. How does that angle work? Okay, again, think about what if theta was 0? If theta was 0, 58.129 would actually be straight up and down, right? And that would indicate that if you measured it here, that would also give you a 0 if it was straight up and down, right? So that's where your theta is going to be. And this is where your theta over here is going to be. Okay. So I need to take into account all of those forces as well. So I have 58.129. I only want the vertical component of it, and it's going to create a clockwise tendency to rotate. So I say minus 58.129 newtons times, okay, the cosine of 65 degrees times what? Okay. But then I also have this FDN. That's going to tend to create a counterclockwise rotation. I don't want the whole FDN, though. I want just the vertical component, which means I have to multiply it by the sine of 65 degrees and multiply all that by 8 meters as well. All right, so that stuff that I have written there is the sum of moments. What do I set it equal to? Okay. You can set it equal to the moment of inertia times alpha. What's alpha? For member BD. Does BD have an angular acceleration? It does not. So that part of the right side of the expression does not have to be included. That does not mean I set this equal to 0, though. Because what do I need to take into account here? I did not sum my moments around the CG. Okay, so I need this kinetic moment term to come in here, right? Which basically means on the, now that I'm on the right side of the expression, I look at those acceleration vectors and I kind of imagine them as forces. That's what I do to do my kinetic moment term. And so I take, for instance, alpha times 2 meters, right? Alpha was 1.25025 radian per second squared times 2 meters. Okay. I don't want all of that. I just want the part of it that is creating this kinetic moment around point B, which would amount to the vertical component, right? Well, the geometry on that is basically the same as what I just identified over here. This is theta right here, and this is theta right here. Okay, so if I want to get just the vertical part of that, I need to multiply it by the cosine of theta. Okay, and you need to multiply by the length as well, right? So you need to also multiply by 4 meters. Okay, and so that actually gives me the acceleration, right? So you look at that, it gives me actually an acceleration times a length. What else do I need? Okay, I need to probably multiply it by the mass, right? So, you multiply this also by that mass of 80 kilograms. Okay? But that's just the alpha part. I also need to look at the component of this that comes about because of the centripetal part, right? Which happens in the opposite direction, the clockwise direction, right? So I subtract 4.4017 meter per second squared. I don't want all of that. I want only the part that points downward. So I multiply it by the sine of 65 degrees. Okay. I multiply that by the length of 4 meters and the mass of 80 kilograms. Now that did make a very long expression there, a very long equation. But what's the good news? It only has one thing you don't know in it. The only thing in it that you don't know is the force at D, FDN, the force there at D, okay, in the normal orientation. All right. In the interest of time, let me go ahead and tell you what this works out to be. You can punch all that in, and I don't think I have any conversion issues or anything in there. I think they're all base units, so it should work out. And it should give you an FDN that would be in newtons. What that turns out to be is, if I can read my notes here, 661.754. This is FDN. All right. Well, so what do I do with that? Well, I can do a few things with it. The first thing I would note that we can do with it is we can go back up to our previous part of this problem. Okay. If I go back up to the previous part of the problem, now I can say this FDN that I have right here is no longer unknown. Okay, I now know that it is 661.754 newtons. Okay, which means that I should be able to sum some forces now in the normal orientation. Okay, when I do that, I'll have FEN minus the component of mg that points along the normal direction there. So I would get mg, m for this part is going to be 20 kilograms. G is 9.81 meter per second squared. To get just the component that points along that normal orientation, I need to multiply by the sine of 65 degrees. Okay, what else? Okay, now I have a minus FDN, and FDN was 661.754 newtons. All right. And what does this equal? Good job. So mass, which is 20 kilograms, times the acceleration of the CG of this part toward E, right? So that part is going to be, or that acceleration is going to be felt right here. Okay, what is that acceleration? Well, it's going to be centripetal acceleration. It is omega squared r. What r would I use? It's rotating around point E, right? It's a fixed axis rotation around point E, which means the radius to it is going to be 1 meter. That means that the centripetal acceleration there is going to be half of what it was out at point D, because it was a radius of 2 out to point D, and now we're a radius of 1, right? So where I had 4.4017 meter per second squared out at point D, that means this is going to be 4.4017 meter per second squared over 2. That's a quick and dirty way to do it. We could go back and we could say we know that's 85 degrees per second. We could do the conversion to radians. We could square that. We could multiply it by the radius of 1 meter. It would give us the same thing. Okay? So we multiply this here by 4.4017 meter per second squared over 2. All right. And when we punch that in, go ahead and punch that in. My print didn't turn out real good right here, so I'll punch it in here. So x minus 20 times 9.81 times the sine of 65 degrees minus 661.754 is equal to 20 times 4.4017 divided by 2. You also got that? Okay. Let's just do a check on ourselves real quick. Did we use the correct direction? So how do I know if I used the correct direction? In other words, does my acceleration direction match the force directions that I was using? Okay, I used FEN to be positive. That should match with the direction I use for my acceleration, right? You can point them either direction you want, but they got to match, right? So this was a little mistake that I made right here. This should actually be negative. Okay. So let me change that up here. All right, 795.55. Okay. Notice here that my direction of my arrow for FEN is opposite the direction of my arrow for centripetal acceleration, right? And I was using the direction of FEN as my positive direction here. So that means I was not matching direction of my forces with the direction of my acceleration. Okay? So now I have matched them because I'm basically saying, yeah, my acceleration there is the opposite direction of the direction I was assuming positive for my forces, which is what my arrows indicate. All right. So that's good. We actually have enough information now to solve for a couple of things. Remember, what we're trying to figure out is force in pins, force magnitude carried in each pin. So we can actually do that now for pins E and D. Okay, so like FE, all it's going to be is just going to be equal to the square root of 49.794 newtons squared plus 795.55 newtons squared. All right. And that gives me 797.11. Can I do that same thing for D? Why, sure. FD is just going to be equal to 58.129 newtons squared plus FDN was 661.754 newtons squared. Okay, and that tells me that my force carried in pin D is going to be 664.302. All right. And those would be interesting numbers to have if you were, for instance, trying to size the pins. Say I need to have the pins big enough to where they're not going to shear. Okay, so, and that's including the dynamic forces that would exist there. All right, well, what's next? What do we lack? We still haven't figured out torque, right? We're trying to figure out this torque value that I have right here. So far, we've come up with the force magnitudes in a couple of the pins, but that's another thing we need is the force magnitudes in pins A and B as well. All right, well, where do I go for that? How about back to this diagram? Okay, on this diagram, how many things left do I have that I don't know? Just two, right? FBT and FBN, right? How many equations do I have left to write? Two. So I'm actually in pretty good shape there. So all I got to do is write those equations. Okay. What I think is probably easiest for us to do here is to write these equations relative to tangential and normal directions. Okay. So we can write a sum of forces in a tangential direction there. For that I have FBT. Okay. May as well put my f dt on there as well. It looks like it goes in the opposite direction, so I say minus 58.129 newtons. All right, because it acts in the same direction as that first one. Then what? Okay, got to take into account everything else that has a component in that direction, which probably means that I should imagine what these angles are going to be. So if I was to draw a line, for instance, right here parallel with that tangential direction, what's that angle between that line and my 116.755, for instance? Yeah, it's still going to be theta, just like it was theta over here, right? What about for my normal direction here, or my, not normal, but for my friction force that I have down here? Okay. Where's that angle supposed to be, you think? Okay, maybe I'll show it like this. Right, there's a kind of a set of axes there, and if I have a, you know, my angle there is going to be right here. Agreed? Okay. I think I might have nicely drawn angles on most everything else. So we'll go through these. The next one being the F sub L, the 116.755 newtons. Okay, does it point in the same direction generally or the opposite of FBT? Opposite, so I say minus 116.755 newtons times, what trig function do I need to multiply by to get the component that points the same direction as FBT? It's adjacent, right? So I take a cosine. Okay, then what? Okay, which is also going to be opposite direction of FBT, right? So I take 116.755. I don't know if I ever got a number for that. Newtons plus 570.989 newtons. All this multiplied by 0.6. All right, and then that multiplied by what? Sine of 65 degrees. All right, what else? Okay. I'll also need to take into account my right force as well as my weight. Okay. Those are also going to be opposite the direction that I had there. So let me kind of start another line down here. I'll subtract. Okay. 570.989 newtons. Oh. And I'll add to that the mass times acceleration of gravity. Okay. But I don't want that entire amount. I want to take just the component that points in the direction of the tangential direction there. So I would take that, all of that multiplied by the cosine of theta. All right. Anything else?
It's confusing that that 58. Oh, we already did that yet.
Yeah, we got that 58.129. It's negative because it goes the opposite direction of the positive FBT that we're putting on there. Okay? So now what? I think I've got all my forces. I set it equal to,
Acceleration.
okay,
Tangential.
yeah,
The sign is correct.
the mass times the acceleration. The acceleration is that alpha, which is the 1.25025 radian per second squared, okay, times the 2 meters. Okay. And when I solve for all of that, it gives me the force at B in that tangential direction. Okay. So, let me punch all that in. X minus 58.129 minus 116.755 times the cosine of 65 degrees minus the sum of those two forces times 0.6 times the sine 65. Okay. Minus 570.989 plus 80 times 9.81 times the cosine of 65. Oop. No. Okay, sorry. Keep adding to this. Is equal to 80 times 1.25025 times 2. Now I can do this. All right, 1254.48. Do you think it's going to look kind of similar for my next one? Probably. All right, so for the next one, it's the normal direction. I have, let me actually do this one such that FBN is pointing in the negative direction. That way it'll match up with my direction I know I have for my acceleration. Does that sound good? So I'll say minus FBN. Okay. Then what? Okay. Plus 116.755 newtons times what? I mean, we could do this in the same, I'll tell you what, we'll do it in the same exact order. I have FDN, right? FDN was what? FDN was 661.754. All right, then I've got 116 would be plus, and so would, that would be plus 116.755 newtons times the sine of 65 degrees. Okay. Then what? Minus 116.755 newtons plus 570.989 newtons times 0.6 times the cosine of 65 degrees. Okay, then what?
570 plus the weight.
Okay, and that gets multiplied by what? The sine of 65 degrees. Then what? It's going to be equal to 80 kilograms times 4.4017 meter per second squared. I just want to check on something here real quick and make sure I have all my terms in that I wanted to.
We need that 58.
Okay. All right. What's that? I do not need the 58.129 newtons because it acts entirely in the tangential direction, right? What took the place of that was the FDN, right? All right, so I have negative, let's see, negative x minus 661.754 plus 116.755 times the sine of 65 degrees minus 116.755 plus 570.989. All that gets multiplied by 0.6 and by cosine of 65 plus 570.989 plus 80 times 9.81, and that all gets multiplied by the sine of 65. This is all going to be equal to 80 times 4.4017. At least if I did it all right. Okay, so 146.29. Is there any of that I should check? Let's see. I think I got all that right. Okay. All right, so 146.296. All right. Well, what can I do with that? Okay, I can find torque if I go in and do a free body diagram of my last link, AB. Okay, actually one of the things I can do real quick here is that FB is going to be equal to the square root of what? Square root of the sum of those squares. That would give me 1262. Point what? 98. All right. Last thing. Another free body diagram. Okay. For this free body diagram, I know that I have an FBT, okay, that acts equal in magnitude, opposite in direction. So that would be 1254.48 newtons. I have the weight that acts in the middle. I have the FBN that acts this way. That's 146.296 newtons. Okay. And then I have my two forces that I have down at the bottom, right? We'll call that FAT and FAN. Okay, I know that I have an alpha around that center of rotation. I know that it's 2 meters. Out to here. I know that this is going to be the mass of 20 kilograms times gravity. Okay. And the other thing that I know here is that I have a torque that's going to be applied around point A. Okay, so what kind of an equation can I write quickly here? Okay, you could write a summation of forces in normal or tangential directions. You certainly could. If what I wanted to get was torque, then I would actually consider writing a sum of moments around point A real quick. Okay, and when I do that, I would have my 1254.48. Okay, that would be in the clockwise direction multiplied by 2 meters. Okay, I would also have the let's see here, mg. So that would be 20 kilograms times 9.81 meter per second squared. Okay, I could pick off just the, with a cosine function, could pick off just the component that was perpendicular to that body, and then I could multiply by how far away it was from point A. Okay, but now I have to add on here one more term. torque. Okay, and this is all going to be equal to what? The moment of inertia about point A, which is the same as what I found for when it was about point E on that other little link. So that's going to be 20 kilograms times 2 meters squared over 3 times what? Alpha. Okay, 1.25025 radians per second squared. Now someone mentioned, what do we need a kinetic moment? Okay, and here's the thing. By taking my moment of inertia about point A instead of about the center of gravity, that takes care of it, right? You don't need a kinetic moment because you're actually evaluating those moments around the center of rotation. Okay, that's a good thing to know. There's two ways to do it, right? You can either take the moment of inertia around the center of gravity, and if you're summing moments around some other point, then you have to add this kinetic moment term. Or if you are summing moments around another point and you know the moment of inertia around that other point, then you just can use that. You don't need the kinetic moment term. All right. So when I punch all of these things in, I can figure out torque. Okay. Minus 1254.48 times 2 minus 20 times 9.81 times the cosine of 65 times 1 plus x is equal to, okay, 20 times 2 squared over 3 times 1.25025. So I need a torque of 2625.22. That's going to be in Newton meters. To drive the acceleration like we wanted to. All right, finding FAT and FAN is really just the same now as we did before, so I'll skip that. You just plug in, now that we know all these other terms, we just plug them in and we can find what those reaction forces are at A. Okay, remember when you do those, you have to keep in mind that the center of gravity of this thing is accelerating, right? Just like we had before on our last link DE, right? We had those two accelerations, and so when you do those sums of forces, you have to not set them equal to 0. You have to set them equal to the acceleration of the center of gravity, just like we did before. All right. That was a long one, wasn't it? Hopefully it was helpful. I will see you guys later.